So, welcome student to the next class of Introduction to Nonlinear Optics and its applications. Today we have lecture number 48. In the previous lecture, we have started one concept called cross phase modulation. So, today we will going to continue that. So, in the cross phase modulation is a process where we know that if two different waves or light beam are incident in a system, then one beam will be affected by other one and vice versa. So, in cross phase modulation, in the previous class we derived the differential equation of the cross phase modulation, and the differential equation of the cross phase modulation we will going to solve today to find out what should be the evolution of the corresponding amplitude and the phase under cross phase modulation. So, this is the extended version of the cell phase modulation. So, let me go back to the slide. So, this is the old slide, and this slide suggests how this cross phase modulation is going to work. So, let me explain once again what is the feature of cross phase modulation. So, cross phase modulation is the change in the optical phase of light beam caused by the interaction with another beam in a nonlinear medium, especially card type of medium. So, this schematic picture we already described in the last class. Again, let me give you the idea what is going on. So, E1 and E2 are the two waves that is propagating together into the medium, and this medium is nonlinear and third order nonlinearity is there. So, chi 3 is dominating here, chi 3 is not equal to 0. When they are propagating together, then nonlinear interaction will take place. P nonlinear will be epsilon 0 chi 3, and then multiplication of E1, which is a frequency of omega 1, plus E2, which is a frequency of omega 2, plus complex conjugate of these two fields, and then cube of that. So, in this way we calculate the P nonlinear. Once we calculate the P nonlinear, then different frequency component will arise. One particular case one can have where in the P nonlinear we have a frequency component omega 1 or frequency component omega 2, and how these two frequency will come we can readily see with this term. So, one term, so in order to have omega 1 frequency in the P nonlinear, essentially we have E2 square E1, this term will come. On top of that there was cell phase modulation term. So, E1 mod square E1 term will also be there. So, if you calculate the corresponding frequency, mod of E1 E2 square should not have any kind of frequency. So, E1 term will contain one frequency which is omega 1. Here also mod of E1 square will not going to have any kind of frequency because this is a mod square, but E1 term again will give rise to one frequency omega 1. So, this entire term will have a frequency component of omega 1. So, if we look the differential equation shown here, then you can see that the similar kind of expression 1 2 term should be here because of this degeneracy factor. Why this 2 term is here we have already explained in the last class. But the thing that you remember that when I am looking for the cross phase or cell phase modulation term for E1, there should be a mod of E1 term here and also a mod of E2 term is there. The first term mod of E1's term is correspond to cell phase modulation, and the next term is cross phase modulation. So, these two term basically there with having a frequency component omega. So, these are naturally phase matched equations. So, there will be no delta k kind of things, because it will cut from both the sides, that you should also remember. And you will have not only one term or one equation, you will also have another equation for E2. The same thing will be done for another wave which is propagating along with E1 with a different frequency, say omega 2. So, we will get a similar kind of expression for E2, only E1 and E2 will replace here, and you will get a set of coupled equation. So, that is the derivation we have done in the previous class. So, today what essentially we do, we just try to solve this and find out what is the effect on amplitude and phase. So, let me go back to the next slide. So, first thing, that if I look these two equation carefully, delta E1 del z, delta E2 dz, these two equations are coupled, and we know that when there is a coupled equation, there is a possibility that energy will transfer from one to another. And in our third harmonic generation or second harmonic generation process, we find that energy is coming from fundamental wave to third harmonic wave, or fundamental wave to second harmonic wave. So, energy is moving from one wave to another. One wave is acting as a pump, and another wave is gaining the energy from that pump. In this case also, we have a coupled equation, two coupled equation rather. One is this one and another is this one. These two coupled equation we have. So, these two coupled equation can exchange the energy. Really they will going to exchange the energy, or the energy will remain conserved, that we are going to find in our next slide. Well, if I consider the energy in terms of intensity, then the intensity, our old equation that we always use, the intensity, let me write it here somewhere, intensity of wave 1 is equal to half epsilon 0 in 1 C mod of E1 square. This is the relationship between the field amplitude and the corresponding intensity. We are using this equation almost every day, so that I can convert the field amplitude to intensity, to make it more to have the physical to have a more appropriate physical meaning. So, now if this is my intensity and I have two equation in our hand, so the next thing is to find out whether intensity of a particular wave, say E1, will remain conserved under cross phase modulation or not. So, the process is, I just need to make a derivative with respect to z of this quantity, whatever is written, and in the right hand side we will do the same. Half epsilon 0 n1 c is a constant term, so it will not going to change. So, here it is, and then mod of E1 square, we will have to make a derivative with respect to z, and if we do that, then we will find it is E1 del E1 star del z plus E1 star del E1 del z. So, this is a standard form. So, we have this. Once we have this, the next thing, this quantity from the cross phase modulation, this quantity is known, and we know that this is equal to I gamma 1 mod of E1 square plus 2 mod of E2 square bracket close E1. This is the differential equation we derived in the previous slide. So, what we will do, we will just put these things here in this equation. If we put these things here in this equation, you can see that in the first equation there is a star. So, if I make a star of that, the right hand side will be the complex conjugate thing. So, I will be replaced by minus I, and this E1 there will be a star. And now, if I multiply that entire thing with E1, so this E1 star E1 will give rise to another term mod of E1 square. And if I put that, then we will have mod of e to the power 4, because this will multiplied by this term and these things will be multiplied by this term. So, we will have another 2 E1 mod square E2 square E2 mod square. In the similar way, if I do the same thing for other term, I will get the same thing except this plus sign. We will have a plus sign here. So, we essentially find that d I dz, if I do this calculation in detail, d I dz, so this term, the first one and the second one will cancel out, and we will have the conservation of individual intensity. That is interesting. In the previous calculation for third harmonic and second harmonic, if you remember, the total intensity was given by the fundamental wave plus say third harmonic wave, and the total intensity was conserved in the system. This was 0. But for cell phase modulation or cos phase modulation, what we find that the individual intensity will remain conserved. So, that means intensity remain conserved means the amplitude of the fields will not going to change. So, what is the physical meaning of that? Let us understand once again. So, we have say this is a block with nonlinearity chi 3. I am launching an electric field E1, I am launching another electric field E2. E1 is containing a frequency component say omega 1, and it is containing a frequency component say omega 2. Both two are launched here. Now, our question is whether the amplitude of these two things will going to evolve over this distance z or not, and we find that at least under cross phase modulation, the individual amplitude will remain conserved. So, there will be no change of amplitudes. Only thing that will going to change should be the phase, because we already have a coupled differential equation in our hand. So, we will going to find that how the phase will going to change. So, first thing we find that in cross phase modulation the amplitude is not changing, or in other way the energy remain conserved. Not only that, the individual energy of each wave is also conserved. Okay. So, once we have the knowledge that individual wave are conserved, the next thing that we are going to do is to find out what will be the effect on phase. So, phase modulation we try to understand under cross phase modulation. So, in order to understand the evolution of the phase or how the phase will going to change, we need to divide our total electric field, the launched electric field, into two parts. So, here this is the previous slide. So, total electric field E1, this is a complex, it is called a complex amplitude, because it should have a amplitude and also a phase. So, if I divide this into two parts, it will be U1 e to the power of I phi 1. This is the standard way to divide any complex amplitude, because we know that E1 is a complex quantity. Once E1 is a complex quantity, then what we do? We just divide into two parts, the amplitude part and the phase part. If you look carefully here, we divide this into two parts, U1 and I phi 1. U1 is a real quantity and phi 1 is also a real quantity, and they are written in the standard way, the way we always write a complex term. It is r e to the power I theta is something like this. Well, once we divide the complex amplitude into two parts, real amplitude and the phase part, real amplitude and the phase part, we are supposed to have two equations in our hand. When we apply these two electric field to our coupled equation. So, this in the right hand side, if you look in the boxes, we have our equations. These are the coupled equations we derived. d E 1 is equal to I gamma 1 mod of E 1 square plus 2 mod of E 2 square multiplied by E. This is our equation. So, what we will do now, we have the field in terms of real amplitude and phase. So, we will going to put these things here. So, when we put these things here, so d E 1 d z, the derivative of E 1 with respect to z will be this quantity, because it is divided into two parts, E 1 and e to the power I phi 1, both are function of z. So, d u 1 d z plus I mod of u 1 d phi 1 d z e to the power I phi 1, just making a derivative with respect to z of this term. In the right hand side, we have I gamma 1. So, I gamma 1 will be there, then mod of u 1 square, mod of u 1 square is nothing but u 1 square, which is amplitude of that. 2 of mod of E 2 square is similarly 2 of U 2 square, where U 2 square, U 2 is the amplitude of the field E 2, and then the total field E 1, E 1 is U 1 e to the power I phi 1. So, from this equation we can see that e to the power I phi 1, e to the power I phi 1 will cancel out. By the way, in the similar way, you can calculate the equation, the amplitude and phase equation for E 2. So, the amplitude and phase equation of the E 2 will come exactly in the same way, and it will have the almost similar form except few changes. So, here is a mistake. So, this coefficient for E 2 will be phi 2, it is again typing mistake, it was written gamma 1. So, it should be gamma 2. So, if you look this equation carefully, so e to the power I phi 1, e to the power I phi 2 will cancel out. Then the rest of the equation, in the right hand side we have a real part and imaginary part. In the right hand, in the left hand side we have a real and imaginary part also, but you can see that U 1 is real, U 2 is real. The square of these two are obviously real, gamma was is real, U 1 is real, only thing is everything is real with a multiplication of I. So, right hand side is completely a imaginary term. Now, on the left hand side we have a real and imaginary term. So, obviously, if I match these two things, so we know the theorem that if a complex quantity is equal to another complex quantity, the real term must be equal to the real term of the left hand side, the imaginary term in the left hand side will be equal to imaginary term on the right hand side. So, here we are using the same principle. So, that means du z, du 1 dz has to be 0, because there are no real part in the right hand side of this equation. So, from here we readily find that u 1 is a constant. That means, there will be no change of the amplitude of u 1, and whatever the value we have in the input, it will remain conserved. So, this is not a new outcome, because in just in the previous slide we have done the same thing, that the intensity of individual wave will remain conserved under cross phase modulation. So, here we are doing a similar kind of stuff. In the similar way, we find that u 2 is also conserved or constant. So, amplitude is not going to change. What about the phi equation? That is interesting. So, in the this right hand side we write the other equation by equating the complex the imaginary parts, and we find that d phi 1 dz is gamma 1 u 1 square u 2 square. So, u 1 u 2 is conserved. So, that is why I write u 1 0 square 2 u 2 0 square, and phi 2 is gamma 2 u 2 square u 2 0 square plus 2 u 1 0 square of that. So, we have a differential equation of phi, and if we solve, and it is non-zero obviously, if we solve we find that phi 1 is this quantity which is a constant multiplied by z. So, that means phi 1 will going to change linearly with respect to z. So, similar thing we have already figured out when we are discussing about the cell phase modulation, how the phase of the pulse will going to modify under cell phase modulation. Here we are having a similar kind of expression in our hand, only thing the additional term here is due to the cross term or the other wave. So, we find the phase is modulated by the pulse itself as well as the pulse that is launched together to the system. So, we will have a phase equation which we derive quite easily and find that under cell phase modulation how the phase will going to modulate, and it will change linearly with respect to z. Well, next let us try to understand one important thing, and that is the nonlinear absorption. So, in the linear absorption is essentially a single photon kind of absorption. So, today we will going to learn the nonlinear absorption, but before that let us give a very rough idea about the linear absorption. So, when a linear absorption is there, so light will going to absorb with a single photon phenomena, and then it goes to the molecule goes to or atom goes to the excited state. In nonlinear absorption normally 2 photons are involved as shown in this figure. So, there is a virtual state, 2 photons are incident to the system and they will absorb, and some kind of excitation will appear here. Since 2 photons are involved, this is related to the intensity square of the system. So, we will see that how these things will happen. So, this is the equation. So, we start with the equation that we derive for cell phase modulation. So, this is the equation that we have derived for cell phase modulation. This is a naturally phase matched equation, and once we have a naturally phase matched equation, so there will be no e to the power I delta k kind of term. So, only the exponential terms are there. So, now what we will do, we just write this susceptibility, third order susceptibility into its complete form, which is the real and imaginary part. So far we are dealing with only the real part. So, now what we will do, that we will introduce the imaginary part also. This is the complete form of the third order susceptibility. It is a real part and also imaginary part. For first order susceptibility also we have done the treatment, where we write it is the real and imaginary part, and find that once we introduce the imaginary part, then basically this gives rise to some kind of loss in the system. Here a similar kind of effect we will going to find. So, we now divide the entire thing into real and imaginary. So, write a total form of susceptibility, and now we put this susceptibility term to here. So, now our equation is chi, in place of chi 3, now I write chi r 3 plus I chi I 3. Total field again divided into 2 part, amplitude and phase. Here I write the amplitude A, which is a function of z, and also phi is supposed to function of z also. And now d e dz, if I do the derivative, because in the left hand side I need to have this quantity, it is nothing but dA dz plus IA d phi dz e to the power I phi. This is the same treatment that we have done in the previous slide. So, just make a derivative just take a amplitude and phase part and make a derivative and you will get these things. Now, we put this quantity here in the left hand side like this, and in the right hand side we write everything and also expand this susceptibility term here. Mod of E1 square is simply a cube, mod of E1 square multiplied by E is simply a cube e to the power I phi. Then once we have this expression, now the next thing that we can do, we can divide into real and imaginary part, and once we divide into real and imaginary part, you can see that this real part e to the power I will cancel out, and this part e to the power di dz will now have one equation in. Previously it was 0 if you remember for cell phase modulation or cross phase modulation, because amplitude was not changing, but as soon as you introduce this term, you can see that there is a contribution for this term and we will have this equation in our hand. So, amplitude, there is a differential equation of the real amplitude and it seems that it will going to change with z. So, the next thing is that to just integrate this differential equation, to solve this differential equation by directly integrating. So, if you directly integrate this differential equation, so it will be dA a cube and right hand side this is a constant, integration 0 to z. So, this integration gives you 1 by a square with the limit 0 to z, then 3 by 4 and then omega, the right hand side is just multiplied by z. Do some simple algebra and you will basically have an expression like this, a0 square divided by az is equal to some quantity. So, this is the evolution equation of the amplitude. So, now if I try to write in intensity in terms of intensity, this a0 I can replace in terms of intensity and also this ratio I can write in terms of intensity also. So, this ratio basically in terms of input intensity is something like this, and now I defined a coefficient beta which is 3 by 2 omega chi 1 3 into square c square and 1 by epsilon like this, and this ratio is simply the ratio of the intensity. And then if I make a slight calculation, then I will have an expression like this. So, this suggests that if we look carefully the expression, this expression suggests that due to the presence of the imaginary susceptibility term, third order susceptibility term, which is here inside the beta, the intensity will going to change and it will decay. So, Iz is decaying. So, it will be decaying like I0 divided by 1 plus beta I0 z. If I increase z, then the denominator will going to increase and you will find the intensity will also decrease. So, 2 photon absorption, we find an expression which is this. So, in 2 photon absorption is the absorption of 2 photon of identical or different frequencies in order to excite the molecule from one state to the higher energy electric state. So, in that case the intensity is all changing and the change of intensity is following this rule. But also we know the linear loss rule, which is normally called the Beer's law. In Beer's law we have an expression like this, which is exponential decay. Now, if I compare these two decay, both the cases the intensity is decaying, it should be something like this. Here this is the exponential decay which is a little bit faster, and this is corresponding to 1 divided by 1 plus z. This is the decay. If I write this is a schematic. This is just to show the idea that how these two decays will be there. So, it is the exponential decay. So, e to the power minus z, and this decay is 1 plus 1 by z. This is the form of the decay. Both the cases, if I increase z, the amplitude or the value will going to decay, but the nature of the decay is not particularly same. Exponential decay will decay faster with this form, whereas in other form, the 2 photon absorption form, the decay will be there, but not as steep as the exponential term. So, with this note, so let me conclude today's class. So, today we have learned two important things. One is the cross phase modulation. The phase is going to modulate, the amplitude will not remain conserved, and next thing is the nonlinear absorption or the 2 photon absorption, where the susceptibility terms as the imaginary component or the third order susceptibility, if the third order susceptibility have some imaginary component. What happened that due to these things we have some sort of absorption. So, this absorption is nonlinear in nature, and that is why it is called the nonlinear absorption. So, let me conclude my class here. Thank you for your attention and see you in the next class.